send that. All right, guys, so here comes balancing equations part 2. I'll put this in context for you in just a moment. But what we're going to do today is we are going to learn about what we call reaction types. What you're going to find out, guys, is that every single one of, every single one of these, all of these reactions, and maybe some of you picked up on this, all of these reactions that you just balanced can all be classified as a type of reaction. And maybe some of you picked up on this. There were reactions where one thing was falling apart. There were reactions where multiple things were creating one thing. There were reactions where something was reacting with oxygen and carbon dioxide and water was formed, which is the one that Sam had us do on the board. There were reactions where these salt compounds were going in and these salt compounds were coming out. There were other reactions where an element was reacting with a compound. And maybe you picked up on that, guys, that there were not trends, but patterns, similarities, better word, in these reactions. And guys, understand that's not a mistake. It turns out that the chemical reactions can be classified. And guys, that's what you're going to learn about today. Now, understand, there are hundreds of different classes of chemical reactions. You only need to know 5. Okay, so guys, that's what we're going to do today. We are going to talk about the 5 types of reactions that you need to be able to keep track of. Then guys, when I see you on Monday, we're going to go into lab and guess what we're going to do? Those 5 types of reactions. And we're going to blow some stuff up. It's actually cute. You'll see. So, guys, so understand, today we're going to give you these conceptually and abstractly, and then when I see you on Monday, we're going to go do them live. And then you'll be writing those balanced equations as well. So, guys, this is the way this is going to unravel for us today. Please don't write this down. So this looks familiar, right? This was out of your notes last time, and here's what we said. We said that when we write balanced equations, it is a 3-step process. But we did these processes backwards. So the first thing, and this was the first part of your homework assignment, is we balanced equations using coefficients. You didn't have to write down the chemical formulas, you just had to make them balance. Then, in parts 2 and 3 of the homework, we then went up here, and you had to write the chemical formulas for the reactants and products, and then balance the equations. We identified that as now and later on Tuesday. Well, guys, today is now next time, because we are now going to engage in the highest level of this process, which is to identify the reactants and products. How do we do that? How do we know what the reactants and products will be? And the answer is we need to know the patterns. So today you are going to learn the patterns. Now guys, along the way there's one thing that we do need to talk about, and this does need to go into your notes before we get into these patterns. So guys, when we write chemical equations, and we understand that these chemical equations, hey, no, I know it's, we're doing sort of a Utah County drug deal. Yeah, it's Cam's, and apparently he's got a buddy that's desperate for Xbox controllers, but he didn't want to interrupt class, so he thought he'd leave them there, and this kid would just come. I know. It actually looks surprisingly like what I do with my dog's poo when I take it for a walk, but I didn't want to say it. And now it's recorded, so yeah. All right. All right. It's frightening how paranoid we've become. Guys, I'm realizing, I take back what I just said. You actually don't need to get this part in your notes because I was looking at my full page. You've already seen this. So, guys, can we just say, are we comfortable with this? This idea that chemical equations represent, and if you don't need to erase it, you can leave it. It's not wrong, it's just you've already done this. So guys, chemical equations we use to represent reactions. what we know right now is we know how to balance these equations. Guys, what we're going to do today is we're going to look at 5 general types of reactions. Please don't write this down. This becomes our to-do list for the day. So guys, what you're going to find out is these are the 5 types of reactions that we're going to learn about today. And some of you look at this and you go, oh good, there's only 5. Some of you look at this and you go, wow, there's 5. Well, guys, if you're the person that looks at this and goes, wow, there's 5, and I'm not going to be able to keep track of that, allow me to offer this as a way to organize these in your head. You'll notice that these first 2 types of reactions have the word in common, displacement. And once you understand what displacement means, obviously some reactions do it once, single displacement. Some reactions do it twice, double displacement. So you can group those together in your brain and it becomes less to keep track of. The next thing that you're going to find out is that these 2 reactions are literally opposites of each other. Synthesis reactions, synthetic, to make. Synthesis reactions put things together. Not surprisingly then, to decompose means to break down. So decomposition reactions break things apart. And then because we live in Utah County and everybody that's a boy is also a Boy Scout, we all understand combustion, right? So, guys, what we're going to do is we are going to group these together in our brains in these groupings. Now, with that said, here's the way this is going to play out. Guys, this is going to become comfortingly repetitious. For each one of these 5 types of reactions, I'm going to give you first a definition. Then I'm going to give you what we call a general form, a clear understanding, I hope, of the pattern. Then I'm going to give you what we call a rule of thumb. It's the thing to look for in order to identify that type of reaction. And then, guys, I'm going to give you an example. And we're going to balance these examples. We're going to think through the process. And then, frankly, these examples are going to become the reactions that we're going to do on Monday. Do you see the pattern? You see what we're going to do? 5 types of reactions, 4 bits of information for each one. When we're done with that, we're done for the day. You'll get some of your homework done. You good? Okay. Now, guys, there's one other thing we need to talk about, and this does need to go in your notes. Write down the word subscripts. Here's the deal. You don't have to do this today. You can't do this today. But you will have to be able to do this on Monday because you'll be in lab. So let's talk. So guys, subscripts are the things that we use to indicate the phase of the things that are in the reaction. Sub means below. They always come second, and we put them in parentheses. So guys, as you're doing the lab on Monday, in addition to recording qualitative data about what you're seeing, you're also going to be recording data that says that was a gas, this was a solid, that was a liquid. Although that's going to be a little confusing because sometimes liquids aren't really liquids, and we'll talk. But guys, understand that you're going to be looking for phases. And not surprisingly, those phases are S for solid, L for liquid, and G for gas. You already know those are the 3 phases of matter. But there's one more phase that you need to be aware of, and this is the tricky one. And guys, that is AQ for, hey buddy, I can, what's that? Are you trying to take the test? Could it be the one that you just recently missed? Okay, I can get you started on that right now. Yeah, that'd be fine. Calculator, periodic table. Okay, so guys, the one that we've got to keep track of is this one, aqueous. If you haven't written any of this down, I would write that down. The abbreviation for aqueous is AQ. For those of you that are bilingual, at least in Spanish, you understand that the Spanish word for water is agua, which has, did I say that right? Probably not. You're laughing at me. Is that? Is that oh good? Yeah, I took 4 years of Spanish in high school from a teacher that was an alcoholic, and she slept through class most days. So it's really true. It was very sad. But I didn't learn. We did a lot of siestas and fiestas, and I didn't learn a lot. But guys, the root word of that is aqua, right? And so we understand that aqua means water. So when we say aqueous, we understand that that has something to do with water. Well, actually, guys, what it means is dissolved in water. So when we have a substance that is dissolved in water, which should sound really familiar because then we're talking about solutions and molarities, tying back to the previous information. Guys, you're going to find that you're going to have, in many instances in these reactions, things that are dissolved in water, and you're going to label those aqueous. You guys good on that? Again, not today, but important on Monday. Good? All right. So guys, with that said, here we go. How is this going to play out? What are you expecting now to happen to you? 5 types of reactions. How many bits of information are you going to be given for each of these? 4. You're going to be given first a definition. Then you're going to be given a general form. Then you're going to be given a rule of thumb. Then we're going to look at an example. So guys, up on the board, and this is where you want to start taking notes again, single displacement reaction. What is it? Well, guys, a single displacement reaction is a single exchange of partners. Now, guys, in order for this to make sense, you've got to understand the word displacement. Watch close. This is the closest that I will ever be to Mr. Ellingford's mad magic chops. You ready? Keep your eye on the coffee mug. That's all I got. That's it. All right, keep your eye on the coffee mug. Did I just displace the coffee mug? No, I moved it. So guys, now watch again. Now I displaced it. What's the difference? Something has to take its place. And Brighton, I love that you use the word replacement, because actually some textbooks call these replacement reactions rather than displacement reactions. So guys, when we look for displacement, we're not looking necessarily for something to leave. We're looking for something to leave as something else takes its place. So with that understood, let's then look at some general forms. So here we go. And guys, understand general forms involve hypotheticals. Can I use that word with you? Hypothetical situations. So, hypothetically, write this down with me. Hypothetically, some element A is reacting with some compound BC. Write it down and then we'll say that again. Some element A is reacting with some compound BC. How do I know BC is a compound? It's 2 things. Now guys, let's remember what we know about compounds. In a compound, which one comes first, the positive or the negative substance? Sodium chloride. Why is the sodium first? It's positive. So guys, in compounds, the positive guy comes first, the negative guy comes second, yeah? So here's then the question. We were told that A is positive. It's a metal. So A is positive. So when these react together, who's A going to hook up with? Positive B or negative C? Negative C. So guys, positive A cannot hook up with B because B is also positive and like charges repel. So A is going to hook up with C. So A hooks up with C. Notice that we wrote A first because A is positive. Here's the sad part. What happens to B? B goes home alone. B is the guy that just got low-crawled at the dance. Someone stole his date, and he's going home alone. Sad, I know. But guys, understand B got displaced. Do you see the displacement? B got kicked out, A ended up with C, and B got displaced. You good on the idea? Questions? Okay. Then talk to me about this. If you don't have questions, and you didn't, you should be able to figure this out. A is now negative. We still have BC, but now we've changed the intruder, if you will. A is now negative. A is now a non-metal. Predict the products without me. Don't be scared. So guys, you're either done or you're stuck, so let's talk. So same thing, right? B is positive, C is negative. That's how compounds work. So A is now negative. So who's A going to hook up with, B or C? I heard both. B or C? With B, because A is negative, B is positive because it's first. So guys, don't write this down if you haven't written anything. But guys, talk to me about what's wrong with this. I've got them backwards. This is chlorine sodium, right? Because we've identified that, that A is negative. And if A is negative, it doesn't go first. So what will the compound be? Ba. So our compound then is Ba, and now C gets displaced. Do you see it? Okay. So guys, with that as a general form, and hopefully now you're more comfortable with this concept of general forms, the rule of thumb, what will you look for to identify a reaction as single displacement? And guys, the answer is this. You will have an element and a compound as your reactants. If you have an element and a compound reacting together, you can be fairly sure that that'll be a single displacement reaction. So guys, in that spirit, there's an element and there's a compound. Here's an example. And again, guys, these examples many times are going to be the reactions we're going to do in lab on Monday. But we're going to talk about these outside of the lab setting now, and you'll go do them in the lab setting on Monday. So guys, how do we know that this is a single displacement reaction other than it's on the slide that says single displacement reaction? Well, here we've got an element, and there we've got a compound. Classic single displacement reaction. So what we need to do is figure out what these dudes are going to do. So maybe then we refer back to our general forms and we start to think to ourselves, okay, there's going to be a recombining of partners. But you'll notice we've got two different ways that can take place. So what do we need to know to figure out what they're going to do? Their charges. So grab your periodic tables. Find zinc. It's in the middle top. It is element number 30. What is the charge of zinc? And you guys all wrote this down with me, right? Because you understand this is important. So guys, zinc, switching colors, is +2. Then guys, we need to know the charges of the hydrogen and the chlorine. We know hydrogen's going to be positive because it's first, and we know chlorine will be negative because it's second. But we need to know not just positive and negative. We need numbers. So what is the positive charge on hydrogen? +1. What the negative charge on chlorine? We don't even have to look it up, right? Because if that's +1, what does chlorine have to be in order to make them balance out? -1. All right. So now we can think about this intelligently. Guys, who is the positive zinc going to hook up with? The positive hydrogen or the negative chlorine? Right? Yeah, the negative chlorine, but check this out. The zinc does hook up with the chlorine, but it doesn't do that. Why not? It ain't balanced. So if zinc is +2 and chlorine is -1, what is the formula for zinc chloride going to be? ZnCl2. But, whoa, wait. There's 2 chlorines and there's only 1 there. Yeah, we'll balance it later. Guys, our goal here is not to keep the equations balanced. Our goal is to write the formulas properly. So now we have to have that sad moment where we realize that somebody got displaced and is going home alone. Who got displaced? Hydrogen. But there's hope, because what do we know about hydrogen and the other 6 elements on the periodic table? They're diatomic, so hydrogen actually hooks up with the buddy and he's fine too. I know. Yeah, so well, you're going to see, you're going to do this reaction, and physically what you're going to see is bubbles of hydrogen. And in those bubbles of hydrogen, those individual hydrogen atoms will have already combined with another one into H2. But now, guys, we've got another problem, don't we? We have just totally disregarded the law of conservation of mass, because we don't have the same amount of things going in as out. But that's fine, because in our homework today, we demonstrated, the homework we graded today, we demonstrated that we know how to deal with this. We have to balance the equation. So guys, we've got 1 zinc, 1 chlorine, 2 chlorines. So we need a 2 hydrogens, and that's balanced. You good? All right. Single displacement reactions. If we can do it once, we can do it twice. Double displacement reactions. By definition, a double displacement reaction is a double exchanging of partners. The general form of it, then, is based upon this foundation. 2 compounds, AB and now CD. But given what you just learned, I suspect you can figure out the products. Take a swing at it. If you can't, that's okay. We'll work together. But I think in building on what you just learned, I think you got a legit chance. Give it a shot. And guys, be careful of charges. Remember, positive guy first every time, right? Okay, so guys, let's try this. We still positive first, negative second. So A is positive, B is negative, C is positive, D is negative. So who is positive A going to hook up with, C or D? D, right? Because A is positive, D is negative. So guys, these two are going to hook up, and one of our products will be AD. Is that written properly? Yeah, because A is positive and D is negative. Now guys, we've got another switching of partners going on where B hooks up with C. But why is BC not the product? Positive first. So how will we write it? CB. So guys, allow me for a moment to step back, because I want you to have this aha. So what we're saying here is that we've got 2 compounds that are reacting together, and they are exchanging partners. And we represented that by drawing these loopy lines that connect these 2 things together with their new partnerships. Some of you right now are sort of having this deja vu moment. Guys, when in this class were you presented with this idea that when reactions happen, sometimes they trade partners in order to form new products? The precipitation lab. Do you remember that? How did you write up the precipitation lab? Well, you took, remember the grid? And you took the positive one from one bottle and the negative one from the other bottle, and you put those together. And then you took the negative one from this bottle and the positive, and you put those together. Guys, every single reaction that you did in that precipitation lab was a double displacement reaction. I couldn't call it that at that time because you didn't know what that was, but every single one of those reactions was a double trading of partners. They were all double displacement reactions. You see the connection? Okay, so guys, what you need now then is a rule of thumb. And what you're going to see with these is you will always have compounds going in and compounds coming out. So now, guys, let's take a look at an example. Unfortunately, this is not, well, unfortunately, this is not the double displacement reaction that you're going to do in lab. The reason is the lead. Lead is really hard to get rid of. We can't dispose of it easily. We certainly can't pour it down the drains because lead is a horrible neurotoxin, which makes us all glad we don't live in Flint, Michigan. So this is not the reaction that we're going to do, which is frankly kind of sad because it is a precipitation reaction and it turns this beautiful, vibrant yellow color. It's really cool. And then the products cause brain damage. Yeah. Mm-hmm. Yeah, that's it. Yeah. All right, guys, so here we go. And because while we were grading homework, we talked about the idea that we're going to be purposeful and methodic with these, we're writing these big, right? So that we're not constrained to these little tiny spaces where we can barely read our own writing. So we're going to write these big, and we're going to give ourselves room to work or play, depending on how you think of it. But guys, give yourself space. So I love that some of you, including Sam right now, are looking at your periodic tables. We have so many Sams in here, it could have been anybody. But guys, looking at your periodic tables, and if you're doing that, what are you finding? Charges. So let's grab some charges. Potassium, element number 19, can only be +1. What does that then mean iodine has to be? -1. Now, guys, we look up lead, element number 82 on the periodic table, and we find that it could be 2 or 4. Which one do we choose? We have to work it backwards. So we look up nitrate on our polyatomic ion chart. Some of you right now are thinking, wait, I thought work it backwards was gone. Work it backwards never goes away. So guys, nitrate is -1. -1 times 2 is -2, +2, +2 divided by 1 is 2. So this is lead 2 nitrate. Now we can figure out not only who's going to recombine, but the ratios in which they're going to do that. So guys, will potassium hook up with the lead or the nitrate? The nitrate. Now, potassium's +1, nitrate's -1. How many of each do you need? 1. So one of your products is going to be KNO3. Wait, it doesn't balance. We've got too many nitrates on the left. That's okay, we'll balance it later. Write the formulas properly first. Now guys, lead is +2, iodine is -1. Where do 2 and 1 meet up? At 2. So how many lead atoms do we need? 1. How many iodines do we need? 2. So guys, we've got our other product, which is PBI2. That's the pretty yellow stuff. That is the ugliest B I've ever written in my whole life. Now we need to balance it. So guys, we've got 1 potassium, 1 potassium, 1 iodine, 2 iodines, so we need a 2. But now that gives us 2 potassiums, so now we need a 2 here. And then we've got 1 lead, 2 nitrates, and 2 nitrates, and that balances. You good? Do you see the connection between single and double displacement reactions? You okay? All right. So guys, now we're ready to go on to the next pairing of 2. synthesis and decomposition. Again, guys, in your brains, group these together, not because they're similar, but because they're opposites, which still makes them similar. But a synthesis reaction is a reaction that creates one product. It takes pieces and puts it together. So guys, the general form then of a synthesis reaction is taking A and B and putting them together. So if it puts them together, what does it make? AB. That's it. What if there was a C? Well, then it'd be A plus B plus C yields ABC. All we're doing is taking pieces and putting them together. So guys, what makes these reactions unique? They have one product. So, let's look at an example. Let's look at a very simple example. Doesn't get much simpler than hydrogen and oxygen. Now guys, the risk in choosing hydrogen and oxygen is it's so simple that you all go, that makes water. But what if it wasn't something as familiar? Well, and you don't need to do this, but hydrogen's +1, oxygen's -2, right? That's why water is H2O. So we still need charges to predict formulas for products, but in this case, technically, we probably don't, because we all know this makes water. So our product is water. But guys, interestingly, that's not our only product. The other thing that synthesis reactions create is energy. And guys, this is true, and you need to know this. This is true of all synthesis reactions. This is actually a general principle in chemistry which your biology teachers actually don't like to talk about and typically teach wrong. In order for atoms to turn into, in order for compounds to form, bonds have to form. And when bonds are formed, energy is released. There's a name for this. You want to write it down. It's called exothermic. Exo meaning outside, thermic meaning heat or energy. So guys, all synthesis reactions are exothermic. The problem is that your biology teachers, have you guys all done biology? Your biology teachers told you this, right? And probably there were little explosions. ATP, adenosine triphosphate, breaks its bonds and turns into ADP. And when ATP turns into ADP, the bonds break and energy is released. Do you remember those little explosions you saw on the screen in Mr. Mauer's class? That is a bunch of phooey. When you break the bonds in ATP to form ADP, energy is taken in. Energy is not released. Doesn't mean the biology is wrong. It just means they teach it to you in a way that's technically incorrect because they don't want to explain to you the whole process. But guys, understand, anytime bonds are formed, energy is released. Every time. That's why they form. So anytime a bond is formed, energy is released, regardless of what your biology teachers told you. Although, frankly, none of you would have made that connection anyway, but I just like to take the chance to poke at biology teachers. So, guys, we got to balance this thing, right? It ain't balanced. So what do we need to do? 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. Is it that easy? That's it. Okay. You guys good? Are you still trying to think through the lies that you've been exposed to in biology classes? Some of you are feeling betrayed. I'll be available after class if you want to talk. Don't expect a hug, though, because I'll go to jail. You guys good? All right. So guys, let's flip the coin. And I don't mean that figuratively. Let's flip the coin. Let's talk about decomposition. So, see if this jives with what you're thinking. Because decomposition then is a reaction that breaks a single reactant apart. Remember, we established earlier that it's the opposite. So if a synthesis reaction puts things together, a decomposition reaction then certainly would break things apart. So, and I'll get you started. What is then the general form for this? Well, your reactant is going to be AB. And then that will fall apart into A and B. Were you kind of expecting that, though? Okay. So what then is the rule of thumb? Well, it's the opposite. If synthesis reactions have one product, then a decomposition reaction will have one reactant. So guys, what I want to do then is I want to give you an example. But I'm going to encourage you to not write this down until we fully form the idea. So check this out. You ready? Are you all caught up? Are you okay? Okay. So guys, here's an example of a decomposition reaction. Familiar, right? Nate, I'm going to have you go over there. Actually, you can go right there. So, guys, we've got hydrogen and oxygen making water and giving off energy. And I hope you're thinking to yourself right now, wait, that is not a decomposition reaction, because what is it? That's a synthesis reaction. But, guys, watch close. Ready? Now it's decomposition. They are literally opposites. You switch, or you know, what else could we have done to switch it around? Just flip the arrow. I used to do that. Actually, it was really fun. It spun. But people didn't quite get the idea. So guys, this then becomes a decomposition reaction. But if you read it for meaning, rather than merely writing it down because you think you should, you may find that this doesn't quite make sense. As a matter of fact, I hope that some of you are reading this and going, no, it don't. No, it don't. Because guys, look at what this reaction is saying. It's saying if you take water and add energy, what do you get out? Hydrogen and oxygen. No, you don't. What happens to your water over in lab when you put it over a source of energy like a Bunsen burner? You don't, well, it boils, right? It turns into steam. But is steam hydrogen and oxygen? What's steam? It's water. Do you understand that? Guys, that when water boils, it's still water. We are breaking intermolecular forces. Wait for it. Guys, when water boils, let me get the salt out of here. So if this is a beaker of water, when water boils, the intermolecular forces break and the water goes away. What, I don't even know if I can do this. What we aren't doing, no, I can't do it. We're not breaking the bonds, right? We are not giving away hydrogen and oxygen. When water boils, it's still water. And that's not what this is saying. This is saying when you take water and add energy, it ain't water anymore. It turns into hydrogen and oxygen molecules, breaking the water apart. So guys, what's going on? If we add energy to water, it turns into steam, which is still water, but this says that's not taking place. And that when we add energy to water, it turns into hydrogen and oxygen. What are we missing? It depends on what kind of energy. Guys, if we add energy to water in the form of heat, what does the water do? It boils. It's released as steam. So the question is actually this: what kind of energy does it take to get water to do this? Do you know the answer? Electricity. If you add energy to water in the form of electricity, it doesn't boil. It breaks apart into hydrogen and oxygen. And guys, I want to show you this. And then if you promise not to tell anybody, I'll tell you a way that you can do this at home. But if you get hurt, you can't blame me. But before we do, I need to share a term with you. Endothermic. This is what is called an endothermic reaction. Endo is in, thermic is energy, takes in energy. Makes sense, right? But guys, what I'd like to do is I'd like to show you this, and then we can talk for a moment about how you might do this at home. But if you choose to do it, you have to follow my instructions. Guys, it looks like this. Are you all caught up? So this, hold on, this music is horrible. No, it's horrible. If you liked it, you're wrong. So guys, this ridiculously expensive piece of glassware, let me sort of zoom up and down it. So there are 3 glass tubes that all meet at the bottom, and down at the bottom there are actually some stoppers, and it's sort of hard to see, but there are electrodes that are connected to wires that go to a power supply. This is what is called a hydrolysis apparatus. $300 to $500 depending on where you get them. I have one that is actually held together with Gorilla Glue and duct tape because a student of mine several years ago wanted to use it to do a science fair project. He was trying to get into the medical school program at Pitt and needed some independent research in order to get in. So I lent him my hydrolysis apparatus because he wanted to use it to do some research, and dropped it. So typically I would do this in front of you, but not surprisingly the Gorilla Glue didn't hold water very long and it don't work no more. But fundamentally the idea is this: these tubes are all full of water and a little bit of salt. Because guys, remember, water doesn't conduct electricity. We've got to add a little bit of something to it to get the current to flow. But when we do, here's what happens. This guy kind of freaks me out a little bit. And guys, when we pass current through this water, can you see the bubbles? Now you can see the bubbles. Guys, these bubbles obviously contain gas, but this gas is not steam. This gas is physically hydrogen and oxygen being formed. Now guys, here's the thing that's interesting, and I think you can even see it from this still image. Which side is bubbling more, the left or the right? The left. Guess what that tells me? That tells me that this pole right here is the negative pole. Think through that. How would I know that? First of all, let's do this. Let's establish why one side is bubbling more rapidly than the other. What is water? H2O. Get it? Twice as much hydrogen as oxygen, right? So when this breaks apart, H2 is formed and O2 is formed, but because water is H2O, you're going to get twice as many H2s as O2s. The one on the left is bubbling twice as fast as the one on the right. Why? Because the H2s are going over here and the O2s are going over there. Why does the H2 go left? because hydrogen is positive and it's attracted to the negative pole of the battery. And you can actually see this. Not only can you see that one is bubbling twice as fast as the other, oh, here's scary guy. How do you get that job? I want to be the... Never mind. So guys, you can see the left one bubbling twice as fast as the right. Tons of bubbles. That's your hydrogen. Not as many bubbles. That's your oxygen. But if you go to the top of the tubes, and guys, there's actually gas trapped up here as well. There's this much oxygen being produced and that much hydrogen being produced. It doesn't quite look like twice because of the constriction. But if you could measure these volumes, you'd find out that in fact you do have twice as much hydrogen as you do oxygen, because this is breaking apart into hydrogen and oxygen gas, and it's H2O. Do you get the idea? And if you're not sold on this idea of H2O, guys, go back to the balanced equation. It's 2, and again, we need to flip it, right? It's 2 H2s and 1 O2. You literally get twice as much hydrogen as oxygen. You good? All right, we got one more to go. Combustion. General form. No, sorry, definition. The definition of a combustion reaction is the burning of a hydrocarbon. Notice this is not carbohydrate. Some people get confused because they're still all spun up about the idea that carbohydrates are carbon and water. Carbohydrates are CN and H2O. These are hydrocarbons, which is simply carbon and hydrogen. As a Boy Scout, your favorite hydrocarbon should be wood, cellulose, and you burn cellulose. But we understand that because we're Utah County Boy Scouts, what is our favorite hydrocarbon? The gasoline that we pour on the wood, because most of our Scoutmasters actually can't start a fire without it. Am I preaching to the truth? All right, so, but guys, in any case, what's going on is this. Your hydrocarbon is reacting with the oxygen in the air, and it's forming carbon dioxide and water. So, guys, this is a real letdown at the end. Your general or your rule of thumb is basically the general form. You've got a hydrocarbon with oxygen, and it always forms carbon dioxide and water. But guys, I would underline like 11 times the words always form. You are going to make these in the homework and on the test ridiculously hard. I'll show you how to avoid it. Can I give you an example? I'm going too fast. Let me at least write down the word example. Are you ready for example? So guys, let's look at a simple example of a hydrocarbon. CH4. Carbon and hydrogen, hydrocarbon, CH4. And let's react this with oxygen. Hey, now it's a combustion reaction. We got a hydrocarbon, we got oxygen. So guys, here's what you then do. Just watch. You look up the charges. Hydrogen is +1. That means carbon's got to be -4. Why is the carbon first? We'll get over it. This is -2. You got to put this with that, and that makes some stuff, and that's sort of water, and then those can't go together anyway because they're +4 and -4, and you get into the middle of all of this on the test, and then finally over here you write, actually no, you'd put a frowny face. You'd put a frowny face because you have no stinking idea what you're going to do, and for some reason you think drawing frowny faces is a good way to communicate to me that you don't know what you're doing. Or you go back up here and you go, oh my gosh, this is a hydrocarbon. Oh my gosh, this is oxygen. I don't have to look up the charges because it always forms carbon dioxide and water. And so I write down carbon dioxide and water. Now understand, the choice is yours. If you like the find the charges frowny face approach, that's your choice. It's wrong, but it's your choice. Or you could just write down carbon dioxide and water and be done. You sensed the sarcasm. So guys, now all we've got to do is balance this. And we've got 1 carbon, 4 hydrogens, 2 hydrogens, so we need a 2. And that balances our oxygens, and we're done. Always forms carbon dioxide and water. You guys good? Can we look at some homework together? Grab your homework packet, y'all. Here, so let me orient you to, well, actually, wait. Okay, so guys, looking at your homework packet, I'm on the second page. It says 2A. You see where I'm looking? And then you'll notice, guys, we've got a page that it says categories of chemical reactions. Then when you turn the page again, it says predicting products of chemical reactions. Y'all with me? That's your homework for tonight. We'll talk more in a minute, but that's your homework. Now turn the page again. 2B. There's another page of homework relative to this assignment. It is not going to be graded when I see you Monday. But if you feel like you need more practice on these immediately, or if you would like more practice on these in preparation for the test, we have given you a second assignment. And guys, watch. The answers are right here. The additional practice assignment, should you lose your packet, and the answers are here. Understand, it's not homework, but it is there for you if you need it. So with that said, go back to 2A with me, would you? Okay, so guys, going back to 2A, here we go. So you'll notice at the top, it gives you the 5 types of reactions. And then guys, there are 20 reactions there for you. And they're all balanced. You're not trying to balance these, you're trying to identify them. Let's do a few together. Guys, what makes number 1 stand out to you? Thinking about our standard forms and our rules of thumb. What is it that stands out about number 1? One reactant, which makes it what kind of reaction? Decomposition. Write it down. Number 2, and you can just put DEC. Number 2, compound, 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 compound. What's it got to be? Double displacement. Number 3, one product. What is it? Synthesis. Number 4, compound, 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 compound. What is it? Double displacement. Number 5, element compound. Compound element. Single displacement. You're going to do that through number 20. Now flip it over on the back. This is where it gets real. Guys, on the back, we have examples of things that read like this. We're going to do the first one together. What this is asking you to do is figure out the reactants, figure out the reaction type, predict the products based on the type of reaction, and then balance it. Again, guys, we're going to be purposeful and methodical with these. Here's what you're going to do. Step number one, you are going to write, and this is number one, do it with me. Step number one, guys, is to write down the formulas for the reactants. Aluminum is Al, sulfate is SO4, aluminum is +3, sulfate's -2. I'm running through these because I know them. If you needed your periodic table and your ion chart to come up with these, that's legit. You'll always have them. Now, guys, where do 3 and 2 meet up? 6. So how many aluminums do I need? 2. So Al2. How many sulfates do I need? 3. So it's S. I want to move that over. Al2SO4. 3. Now, guys, similarly, calcium is +2, phosphate is PO4 with a -3 charge. Again, where do 2 and 3 meet up? 6. So that means I need 3 calciums and 2 phosphates. Now I've got my reactants. If you're right now sitting there thinking, whoa, I don't remember how to write chemical formulas, you're going to get lots of time to practice. Now, guys, at this point, now that we've got the reactants identified, we need to now figure out what type of reaction this is. So, guys, do this with me in your head. Ready? And we're going to do them in the order we learned them. Could this be a single displacement reaction? Why not? It's not an element in a compound. Just grab a seat, Connor. We'll talk in 2 minutes. Could it be single displacement? No. Could it be double displacement? Compounds, yeah, certainly. But we can't stop there. Could it be synthesis? Yes. If it was synthesis, however, what would the product be? One really big thing, right? Could it be decomposition? No, because a decomposition reaction is one thing falling apart, and we've got 2 things. Could it be combustion? Not even close. None of this is hydrocarbon or oxygen. So, guys, now we've narrowed it down to double displacement or synthesis. Which one's it gonna be? Double displacement. Because if it was a synthesis, we'd have to put all those things together, and we can't do that. So it's double displacement. So we come over here to the left and we go DD for double displacement. Now we've got to figure out our products. You're in an advantage because you've got a lot of paper. I'm running out of space, but here we go. So guys, this is the way this works. We need to know who hooks up with whom. So we'll hook up the calcium and the phosphate. Because positive and negative, you can draw the line if you want. That means the calcium will hook up with sulfate. So now what we need to know is charges. Ready? Aluminum is +3, phosphate is -3. How many of each do we need? One aluminum, 1 phosphate. Then, guys, the calcium and the sulfate hook up. Calcium is +2, sulfate's -2. How many of each do we need? 1 of each. CaSO4. Now, guys, we need to balance this thing. So here we go. 2 aluminums, 1 aluminum, so we need a 2. 3 SO4s, 1 SO4, so we need a 3. Now we've got 3 calciums, conveniently 3 calciums, 2 PO4s, and conveniently 2 PO4s, and that balances. And guys, that's not convenient. That's the way these things work. Because they're reorganizing based on their charges, these things balance relatively simply. So guys, you've got a homework to do and not much time to do it in class. Do not make the mistake of trying to do this assignment Sunday night. You will remember nothing. Do it tonight. Come in tomorrow when you need help. Although, guys, I should tell you, I won't be here tomorrow. I'm taking my wife to, I'm taking my wife to a marriage retreat. We're going to sneak off to Boise for the weekend and just get to be not parents for a weekend. So, guys, I will not be here tomorrow. Mrs. Clay and Miss Call will be around. Use them as resources. We will grade this on Monday. We will do a lab on Monday. Have a good weekend. And, guys, don't wait till Sunday to do these. Please. That is all.